That's good. Okay, cool. So today I'm going to be talking about using machine learning to increase equity in healthcare and public health. And I think after that introduction, there's not a huge need to motivate why this is important, right? Of course, healthcare and public health, enormous inequities remain. It's also the case that algorithmic approaches have worsened that inequity at times. There's certainly no panacea to social inequality. This paper is maybe the most high-profile recent example of this, but there are many other examples as well. I think this is probably familiar to you, so I'm not going to belabor that point. I will say, though, that my research has often pursued a more optimistic counterpoint, which is that algorithmic approaches properly applied can also be used to reduce health inequity, and that will be the focus of my talk today. In a very broad way, my work sort of pursues two paths to using machine learning and data science to increase health equity. The first is, how can we use it to sort of de-bias decision making? And I've looked at that in various contexts, from sort of detecting bias in policing to many other contexts as well. The other path I've explored is using machine learning and data science to better understand the health of understudied populations, people who historically have been sort of ignored by medical research. This includes, for example, women, socioeconomically disadvantaged populations, et cetera. And as mentioned, I've modeled various things in these populations, from COVID to pain and various other things as well. Today, I'm going to be telling you three stories from sort of this broad area. The first is about policing, and it turns out the math on medical testing is quite similar. So there are connections to both health equity and sort of public health. Then I'll be talking about intimate partner violence. And then finally, I'll be talking about sort of a hot button question in the clinical community right now, which is, when should we use race as a predictive feature in clinical algorithms? Looking at this hodgepodge of stories, you may wonder, is there any unifying ideological idea here, or are you just sort of showing us random things? Turns out there is, in fact, a methodological connection here, which is rare in my talks. So count yourselves lucky. And sort of the unifying principle here is that all these things are about missing data and its connections to health inequity. It turns out these connections are myriad and profound. The first two stories are about missing data and its connections to understanding human biases, so sort of biases in human decision-making in healthcare. And the last story is about missing data and its connection to algorithmic bias, and specifically the design of clinical algorithms. So I'll say, by the way, that as I suspect many of you know, the missing data problem is like a very hard problem. It's sort of unsolvable in full generality, and to me, it's also often sort of been a fascinating problem. Actually, my work when I was in England was very much on missing data and censored data, and that was 7 years ago or 8 years ago, and I've still been thinking about it. And so in the way that you sort of get obsessed with a thing and you can't quite let it go, and so then you talk to everyone about it until they're thoroughly bored. This is sort of a cry for help in some sense. Okay. Good. So let's talk about policing and medical testing. And this is joint work with a number of excellent co-authors, and it's based on several papers. So policing is a public health issue, and I'm going to be talking about policing in the United States, and I'll try and give relevant context along the way, because I know it's somewhat different than policing in England, and often in worse ways. So in the United States, policing is a major cause of death for young men, particularly for young African-American men. And today I'll be talking to you about police traffic stops. Why do we care about traffic stops? This is one of the most common ways that Americans interact with the police, with tens of millions of Americans stopped every year. And on at least some occasions, those stops will sort of escalate into high-profile incidents of violence, basically. Like a substantial number of police killings of Americans have originated in police traffic stops. And there's concern, of course, that traffic stops may be racially discriminatory. And to be clear about what I mean by racial discrimination, this is when someone is treated more negatively on the basis of their race. So, for example, they're stopped by police because they are Black. They would not have been stopped had they been driving identically, but they've been white. And there is, as I suspect you know, abundant prior evidence of racial biases in police stops in the United States, right? That ranges from sort of econometric and statistical evidence to sort of evidence from sociology to the lived experiences of Black and Hispanic drivers. This has been documented in various contexts. But in the United States, it's been very hard to quantify this on a national scale for various reasons that I will describe. And so this is the goal of this project, to sort of embark on a large-scale quantification of racial discrimination in police traffic stops. So Why is this challenging to do? Well, the first basic challenge is that somewhat astonishingly, like there is no national traffic stop data set that sort of tracks every stop made by the police in the United States, which might be surprising given like how important this is. But in fact, the way data is tracked in the United States is that every state and local police department tracks it in its own idiosyncratic siloed format. So in the first step of this project, we worked with our journalist collaborators to submit data requests to more than 150 police departments over the course of 5 years. And, this is about as much work as it sounds like. Like journalists are pretty remarkable, just incredibly, diligent, fastidious, persistent. If you have data you don't want to make public, like don't get journalists involved, basically, like they are really tenacious. And so then like the data all comes pouring in and you have sort of the data standardization task out of like nightmares. Like literally this is still a little triggering to me to talk about, right? Like every department encodes data in a different format. There are like numerous, errors and to summarize, it's like tens of thousands of lines of code, thousands of hours of cleanup. But I'm not actually going to tell you about any of that today. I'll just say we've made all that data available so you can analyze it yourself. And the data set spans hundreds of millions of traffic stops. It can be just downloaded off the internet. And our main analysis encompasses about 100 million traffic stops. The reason that number is somewhat smaller is that we restrict to the states where you actually have enough data to even analyze racial discrimination. For example, some states don't track race of the driver at all because we don't racially discriminate. So why would we track race? That obviously makes it hard to analyze racial discrimination. Okay. So our analysis looks at 3 questions. We look at whether the police discriminate in whom they stop in the first place, whether they discriminate in whom they search after a stop, and then finally, how do policy changes, specifically the legalization of marijuana, affect these racial disparities? Today, I'll only tell you about the second question. You can find the other 2 in the paper. And I'll focus on this because the methods are applicable to studying bias in many other decisions, including, as I'll discuss, medical testing. So, are police searches discriminatory? A little bit of context about how police searches work in the United States. So after the police stop a driver, they're allowed to conduct a search. And the purpose of that search is to find contraband. So things you're not supposed to be carrying, basically. So illegal drugs, weapons, etc. The purpose of a search is to find contraband. It shouldn't be to like harass the driver or meet some quota or whatever. And so what we test for is, are minority drivers searched when they are less likely to have contraband, so at a lower threshold of evidence. So for example, if police are searching white drivers when they're only 90% likely to have contraband, but black drivers when they're only 10% likely to have contraband, then that difference in thresholds is discrimination under our definition. Importantly, this is not comprehensive, right? There are many other ways that police could behave problematically. This definition, for example, says nothing about disparities in police use of force after a stop, right? And that's one of the reasons we've released all the data publicly, because a single paper can only sort of scratch the surface of what is possible with this data. Nonetheless, it is an important definition of discrimination, and so that's what we're looking at here. Now, to link back to missing data, it turns out this is in fact a missing data problem. Why? Because we only observe the outcomes of searches for the people the police historically searched, right? So like if the police don't search you, we don't know whether or not you were carrying contraband. So we only observe this outcome for a biased subset of the population. In other words, the outcome data is censored by human decision-making. And this is tricky, right? Because the humans are, of course, potentially biased, right? They might be, using all kinds of decision functions to decide whom to search. But also, humans potentially have access to unobservables that we do not observe in our data set. So I don't know, whether the driver is acting nervous, for example, might be both relevant to the police officer's search decision, but also to whether the driver carries contraband. All of these things mean that the unsearched population may be very different from the searched population. We cannot, for example, simply train a model on the population with outcomes, the searched population, and assume it generalizes to the unsearched population. This problem has been known by many forms in various literatures. The term I'll use here is a selective labels problem, which is introduced in a paper a couple of years back. But like in various forms like statistics, econometrics, et cetera, this has been studied for a long time. And problems of this form appear in many domains besides policing, as I'll discuss, including hiring, lending, medicine, etc. So this is a very, very broad problem. Okay, so how do we look for bias in police searches? The first thing which has been proposed is look at how likely members of different race groups are to be searched. So basically, look at search rates broken down by race. And when you do this, you do in fact see that Black and Hispanic drivers are more likely to be searched after a stop than are white drivers. So, the disparities are large. I've shown them at right. They appear in both state stops, city stops, etc. But this by itself doesn't necessarily prove that the police are discriminating against Black and Hispanic drivers. It is possible that some race groups are more likely to carry contraband. The purpose of a search is to find contraband. So if there are group disparities in how likely people are to carry contraband, the police may be more likely to search those groups simply in the course of normal policing, even absent discrimination. So addressing this issue, which has been recognized for a long time, people have proposed what's called the outcome test, which says, don't look at how likely different groups are to be searched, look at how likely those searches are to find contraband. We call this the hit rate. And the intuition here is like, look, if searches of white drivers are finding contraband 90% of the time, but searches of Black drivers are finding contraband only 50% of the time, it suggests that the police are searching white drivers only if they're really, really likely to carry contraband, but they're searching Black drivers on the basis of less evidence, suggesting discrimination. So if the hit rates vary by race, and if in particular they are lower for minority drivers, this suggests discrimination under the outcome test. And when you look at the data, this is in fact exactly what you see. You see that the hit rates are lower for Black and Hispanic drivers, suggesting discrimination under the outcome test. Turns out, though, that there is a statistical issue with the outcome test as well, and this is known as infra-marginality. And I'll illustrate this with a simple hypothetical example. All these numbers are totally made up. This is a stylized example to illustrate the statistical flaw. Imagine there are two races of drivers, Black drivers and white drivers. And among each race, there are two easily distinguishable groups, like maybe one of the groups is wearing hats. There are the drivers who are likely to carry contraband, and the drivers who are unlikely to carry contraband. And among the likely drivers, 50% of Black drivers carry contraband and 75% of white drivers carry contraband. Among the unlikely group, 5% carry contraband, irrespective of race. And importantly, imagine in this hypothetical example that the police are not being discriminatory. They apply equal thresholds by race. They search everyone above a 10% threshold of likelihood of carrying contraband. So what's going to happen to the hit rates for white and Black drivers? Well, the police are going to search, basically everyone who in the likely group, right? And so they'll end up with a hit rate of 50% for Black drivers, 75% for white drivers. So it will look under the outcome test like there's discrimination, even though by assumption in this hypothetical example, the police are applying the same threshold to everyone, irrespective of race. And the outcome test can also yield misleading results in the other direction, where it fails to find discrimination, even though in fact it is occurring. So why is this happening, right? Why are we getting these misleading results from the outcome test? It's happening because the statistic we're measuring, the outcome test measures, which is the probability of carrying contraband, conditional on being above the search threshold, is not the same as the statistic we actually wish to measure, which is the search threshold itself. Those are simply different quantities. But that search threshold is not easy to measure. It's a latent quantity. It's not a simple fraction directly observable from the data. And so the solution that's been proposed is to use a Bayesian latent variable model to attempt to infer this threshold. And so I'll describe that model to you now. This is what's called a threshold test. It proposes a stylized model of a police stop, so it doesn't aim to capture every sort of feature of the stop, as no statistical model can, right? But hopefully enough of the features to sort of give you a realistic inference. And in particular, the goal of the model is to estimate these search thresholds in a way which is consistent with the observed data, namely the search rates and the hit rates. And discrimination under this model is if lower search thresholds are being applied in searches of minority drivers. So, if the police are searching Black drivers when they're only 10% likely, but white drivers only when they're 30%. So how does the threshold test work? Basically, the threshold test, the way it models a police stop is, we imagine that when the officer stops the driver, they estimate the probability P that person carries contraband. And P is drawn from some risk distribution, which is a probability distribution on the unit interval. I've shown that graphically at right. So for example, if the police officer, stopped a bus driver, it would hopefully be quite unlikely the guy would be carrying contraband. He's driving kids around. And so, hopefully not also driving drugs or whatever. And so P would be quite low. In contrast, if the police officer stops a woozy acting driver, and he's drinking out of a bottle, then P might be higher. So P is sort of a summary of sort of all the observable features of the driver at the time of the stop and the probability. So if P exceeds a threshold, the officer searches the person, and if they search the person, they find contraband with probability P. So in the case of the bus driver, he'd be below the threshold, the officer wouldn't search him, wouldn't find contraband. In the case of the woozy acting driver, he'd be above the threshold, the officer would search him and would have a 75% chance of finding contraband. The model allows the thresholds and the risk distributions to vary by race and location, and discrimination, as before, as if lower thresholds are being applied in searches of minority drivers. In order to complete the probabilistic specification here, you basically have to specify how do these latent quantities, the thresholds and the risk distributions, map to the observed quantities, namely the search rates and the hit rates for each race and location. Turns out that there's a fairly simple parametric way to relate these two. You can write the search rate as sort of the amount of mass to the right of the threshold, and the hit rate as sort of the conditional mean, so the expected value conditional on drawing from the gray mass. There are a lot of other mathematical details here, regarding inference, what sorts of priors to use, etc. But I'm going to sort of skip over those. Feel free to ask more if you're curious about them. But broadly, it's sort of a Bayesian specification, and you infer the posterior over the parameters using MCs. Turns out that this actually doesn't work at all in a data set of our size using the original sort of parameterization of those risk distributions. The original threshold model tried to write down the risk distributions as beta distributions. It turned out computing the requisite quantities and also their gradients, because that's what you need for Hamiltonian Monte Carlo, was prohibitively slow. This had a couple practical implications. The first is that we couldn't fit the model on a data set of our size. And the other was that it really limits the applicability of the test in terms of what real world practitioners can really use it. Journalists can't use it, for example. Anyone who doesn't have sort of a large cluster and a bunch of PhD students willing to stare at a screen for a long time is not going to be able to apply this. So what we did in subsequent work was write down basically a new family of probability distributions, which rely only on Gaussians. A general lesson of my PhD is that everything is nicer when you use Gaussians. And this turned out to make inference about 2 orders of magnitude faster. The full details of that are a story for another time, but I guess a high-level takeaway is that this is a case where sort of probability distributions, have practical implications, right? They make inference much faster, and that means that this test can be used for more people and on larger data sets. With the fast threshold test, we were able to fit a national model, and I've shown you the results here. The model does infer that lower thresholds are being applied in searches of Black and Hispanic drivers, suggestive of discrimination. So to summarize, I've sort of told you 3 results of our search analysis. And this is a characteristic pattern for sort of discriminatory searches. You'll see it, for example, if you look at stop and frisk, the stop and frisk policy in New York City, which was a large scale sort of search policy that was found to be unconstitutional for reasons of racial discrimination by a federal judge in 2013. The pattern basically is that search rates are higher for minority drivers, hit rates are lower, and thresholds are lower. So all 3 tests here are sort of reassuringly pointing in the same direction, suggesting discrimination against minorities, but the threshold test is sort of doing so in a way which is robust to the statistical flaws of simpler tests. To speak briefly about the public policy impact and sort of non-academic impact of this work, in 2019, some journalists were able to take this sort of fast version of the threshold test with some help from our team and use it to show that the Los Angeles Police Department was searching Black and Hispanic drivers on the basis of sort of lower thresholds. And in response to that, this is kind of why journalists are nice, because they don't just write papers that no one can read. The LAPD, the Los Angeles Police Department, announced that they would dramatically cut back on pulling over random vehicles in an effort to reduce this racial bias. Okay, now to speak briefly about how these selective labels problems appear much more broadly, you can actually apply the exact same math in other data sets where you sort of observe some binary human decision, and for sort of the subset who got the positive decision, you observe the outcome. So for example, in the lending context, the binary decision might be, does the bank grant the person a loan? And the outcome would be, does the person repay the loan? And discrimination might look like minorities are less likely to receive a loan from the bank, but more likely to repay it conditional on receiving it. In medical tests, the decision might be, does the doctor give the patient a test? And the outcome might be, does the patient test positive if they're tested? And sort of bias in this context would look like, minority patients are less likely to get tests, but more likely to test positive conditional on being tested. And so, this is sort of a setting with very broad applications and a lot of applications to bias. And, so they're very important. They're also like unsolved, as mentioned, this has sort of been an active, difficult, open problem in a number of literatures for a very long time. And in particular, this problem is unsolvable without, I just had to move my cat. In particular, this problem is unsolvable without further assumptions. Why? Because otherwise the untested people, they could all be true positives, they could all be true negatives. You just don't know, right? In my opinion, and sort of based on thinking about this problem for a while, domain-specific solutions are probably necessary because which assumptions are reasonable will vary by domain. So in policing, you often don't have a lot of data, sometimes you only even have aggregated data. You don't even have individual data. And so you have to sort of make strict parametric assumptions to allow the threshold test to work on the basis of little data. In contrast, in medicine, that may not be the optimal solution because the data can be much richer and more detailed. You might have lots of covariates, which could inform your inferences about the shape of the risk distribution. You might also have other sources of side constraints, sort of ways you can constrain the unobservables. And so that is something we are actively looking into now. I will mention, just as a quick sneak preview, is that our preliminary work, sorry, all right, this is, I have two cats on my desk and they're trying to fight with each other on my desk, which is not good. Our preliminary work has shown evidence of bias in COVID-19 testing. So basically we took the exact same work, I took the exact same playbook, applied it to COVID-19 testing in the United States, and it basically found that Black and Hispanic patients were receiving COVID tests only at sort of higher search thresholds. And I'm quite interested in sort of studying that using actually better data in the UK. The UK Biobank has done some pretty heroic linkages between your COVID data and between UK Biobank data, and I think that's an exciting direction for follow-up. And actually, if anyone wants to talk to me about that, I'd be very happy to chat because I don't quite totally understand all the peculiarities of how COVID testing and COVID reporting in the UK works. And, very happy to chat about that. Okay, but in the interest of time, I'll go on to the second story. This is one about intimate partner violence. This is work led by Divya Shanmugam, who's an excellent MIT PhD student who will be on the job market actually pretty reasonably soon. So you should definitely think about hiring her if you can persuade her to come to England, or don't, because then we can hire her at Cornell. Okay, so the goal of this work is to assess the relative prevalence of underreported conditions. What does this mean? So what's the relative prevalence, first of all? Relative prevalence is just how much more common is a disease in one group versus another group. So here, I've shown you the relative prevalence in Black versus Asian patients. And, for example, this disease affects in Black patients, 4 patients out of 9, in Asians, 6 patients out of 9. And so the true value would be 4/6. This is very easy to do if the disease is perfectly observed. Of course, it becomes much more challenging though if you have underreporting in a way that varies by group. So now let's imagine that rather than observing true patient status, we observe only sort of a diagnosis which doesn't perfectly diagnose everyone, in particular underdiagnosis. So only a subset of true cases are diagnosed as such. Here, if we just look at the observed data, we're going to get the wrong value for the relative prevalence. So why do we care about relative prevalence at all? Why is this an important problem? Basically because it's essential to sort of pass efficient and equitable health policy. Here's a case study of this. In the 90s in the United States, there were reports describing how Native American populations were much more likely to suffer from diabetes. And in response, Congress established in 1997 the Special Diabetes Program for Indians. And as a consequence of this, there was a huge decrease in diabetes-related complications in Native Americans. So this was something where sort of accurate estimates of the relative prevalence quite directly translated into improved and more equitable health outcomes. Okay, so why do we care about underreported conditions? I'm sorry, I'm gonna have to move these guys because it's just impossible to. Yeah. My apologies. Give me 30 seconds. That's better. I'm so sorry. Usually they're much quieter, but they got riled up. That hasn't happened during a talk before. Okay, so why do we care about underreported conditions? As you probably know, if you're familiar with health work, it's because they're like so ubiquitous, right? Many important medical conditions are underreported. And the condition that motivates this work is intimate partner violence. Both Divya and I read this book, which I would highly recommend, although it's a somewhat difficult read, as you might imagine, entitled No Visible Bruises. And this is sort of about how intimate partner violence is so ubiquitous and so often entirely invisible. But this is true for many other conditions as well, including many other women's health conditions. So this is why we care about sort of accurately measuring the relative prevalence even of underreported conditions. Now, the setting we're in here can be formalized as what's called positive and unlabeled learning, or PU learning. And if you're not familiar with PU learning, there's a pretty excellent survey paper on it, which gives a nice overview of the field. But I'll summarize it briefly for you the setting now. Basically, we assume that we observe two types of patients. We observe true positives, the people who really have the medical condition, and then we observe unlabeled patients. Because the condition is underdiagnosed, this might consist both of true positives and true negatives. So, basically, you don't know if the people who aren't diagnosed really don't have it or just weren't diagnosed with it. So this is widely used to model underdiagnosis. And the sort of implicit assumption here is that there are no false positives. So anyone who is truly labeled as having IPV, intimate partner violence, truly has it, but not everyone who is labeled, not everyone who truly has it is labeled as having it. So you might ask, clearly this is a missing data problem, right? You don't observe the true diagnosis. You don't observe the true disease status for everyone, right? Only a subset of true positive cases are diagnosed as such. You might ask, well, how does this setting, the PU setting, compare to the selective label setting you were just telling me about? Turns out it's harder. Selective labels is already hard, so this is bad news. How can you see it's harder? Well, in the selective labels setting, right, you observe true positives, true negatives, and unlabeled, right? So basically, for the people who are tested, you know whether they're positive or negative, so you observe both true positives and true negatives. And then for the people who are untested, those people are unlabeled. In contrast, in PU learning, you observe only two groups. You observe the true positives and the unlabeled. So, selective labels is hard. This is harder. So we're definitely going to have to make some assumptions to make any progress, right? Missing data is hard. To give a little more intuition, sort of independent from selective labels for why you need assumptions here, let's say you see that a disease is very rarely diagnosed. Without further assumptions, you cannot tell the difference between two worlds. One world is this disease is truly rare, and the other world is this disease isn't rare, it's just underdiagnosed, right? You can't distinguish between those. Those are observationally equivalent without further assumptions. One frequent assumption that past work has made is that the positive and negative class, the true positives and true negatives, are at least somewhat separable. In other words, there is a region of feature space where there are only true positives. And the reason this helps is that if you can assume that that region exists and that you can identify it, then you can just look at what fraction of examples in the space are positively labeled. And then if you're willing to make the further assumption that that label frequency remains constant, you can back out the overall label frequency, so sort of the probability that a true positive is diagnosed as such, and then from that sort of figure out the true prevalence. But it's really not that plausible in medical settings that we're going to have some magical region of the feature space where you definitely have the condition, right? Often many conditions only have sort of non-specific symptoms, for example, where they might indicate one of many health conditions. And certainly, that's true of intimate partner violence too, where it's if someone shows up with injuries, they could be indicative of IPV, but they also might be indicative of other things. So our contribution here is to propose relative prevalence estimation as sort of a novel task in the PU learning setting. Previous work has largely focused on relative prevalence estimation, but on absolute prevalence estimation. We provide assumptions under which you can recover the relative prevalence, which we think are more plausible in medical settings than the separability assumption. And we provide a method under which, that actually applies these assumptions. And we provide checks for the assumptions, and then we show that the method works reasonably well on synthetic, semi-synthetic, and real data. So to give the high-level intuition for this method, this is sort of the no math version. Let's say you want to know about the relative prevalence in IPV in Black patients versus white patients. But as mentioned, IPV is underdiagnosed and furthermore in a way that may vary across races. So you can't just take the ratio of diagnosis rates, but you can learn which symptoms are suspicious for IPV, right? You do have a few labeled cases, and from those people, you can learn sort of what symptoms tend to characterize IPV. Then, if you're willing to assume that that suspicious symptom model remains the same across races, you can back out the relative prevalence. And the rough intuition is the race group that has the higher prevalence of suspicious symptoms has the higher prevalence of the condition. To be a bit more formal about that, we assume basically that the unobserved latent thing that we really care about is denoted by Y. These are the true labels. Has a patient really experienced IPV? The observed data consist of S, which are the observed labels. So this is whether someone is diagnosed with IPV. X, the observed features, which are the patient symptoms, for example, their ICD codes. And then G, which is the patient's group. And this is sort of what we care about inferring the relative prevalence across. So it might be their age or their race or their insurance status. And the PU assumption in this setting, the no false positives assumption, is that if Y is 0, then S is never 1. So how does our method work? Basically, we model the probability that a patient is diagnosed with the condition given their group and their symptoms. And importantly, this is fully observable from the data, right? We know S, X, and G, and so therefore we perfectly observe this thing. And we model this thing as the product of two terms. The probability the patient truly has the disease given their symptoms times the probability that they are diagnosed given that they have this disease. This decomposition only holds under a set of certain assumptions. We assume that the first term remains constant across groups. So this is one of the assumptions underlying our method. And then the second term we allow to vary across groups to allow for underreporting. Now, staring at this decomposition, you'll notice that you actually can't recover either of the two terms on the right-hand side exactly, right? Because you can always take the first term and multiply it by 2 and the second term and divide it by 2, right? So you've got this fundamental sort of multiplicative unidentifiability. Turns out, though, that you actually only need to compute PY given X up to a constant factor because the relative prevalence is given by this expression. So if you're off in estimating PY given X by a factor 2, that's just going to be the same in the numerator and the denominator, and it'll cancel out. And so this is the sense in which sometimes you can estimate the relative prevalence, even if you can't get the absolute prevalence in either group. All of this only works under 3 assumptions. I'm not going to go into detail about these now. I'll just list them for you now in the interest of time. But I'm happy to chat more about how plausible they are. If you want to know my honest view, I think they are a useful complement to existing assumptions. They're not going to hold in all settings because this is just a very hard setting. Basically the 3 assumptions are no false positives. So this is just the standard PU assumption. Random diagnosis within groups. This is what's called the SCAR within groups assumption, very commonly made in this setting, probably doesn't always hold. And then finally, that the probability you truly have a condition, given your symptoms, remains constant across groups. Okay. So does this work? Basically, we show it does in various settings. We start with synthetic and semi-synthetic data. The reason we use this is because we want to be able to observe Y, the true disease state, so we can assess the accuracy of our relative prevalence inference. And we show that sort of relative to other baselines, our method, which we call purple, so this is this dot all the way on the right, is able to more accurately recover the true prevalence. The other dots are baselines. Green is the oracle that you can't actually apply on real data. And you want to be on the dotted line, indicating that you're perfectly recovering the true relative prevalence. And sort of purple is the only method that on both separable and non-separable data performs comparably to the oracle. We also look at semi-synthetic data. So basically we take sort of the distribution in high dimensional real health data, and we use it to generate the true disease state Y. We do this in 4 different ways, sort of simulating 4 different diseases to examine a realistic range of cases. And in all cases, we sort of find that purple is able to continue to recover the relative prevalence. Here again, our method is sort of consistently lying across the dotted line, indicating perfect recovery of the true relative prevalence, whereas other methods are not at all consistent. We also do some work in sort of the settings where our model assumptions are wrong, because as I mentioned, this is a hard setting. Assumptions are not going to hold in all cases. I don't want to overclaim there. And specifically what we do is we provide 2 checks for modeling assumptions. They won't rule out all violations of the model, but they will rule out some violations of the model. And we describe what you can do to kind of apply those and try and not apply our method in cases where the assumptions clearly don't hold. We also show that even if the third assumption is violated, that covariate assumption is violated, we still are able to sort of provide a useful lower bound on the magnitude of disparities. The reason a lower bound is helpful is because you can say something like, look, I estimate that this disease is at least twice as likely in this group. It could be that it's 3 times as likely, but regardless, you should probably be prioritizing these folks. And then finally, we take our method and we apply it to real IPV data where the true, we don't observe the true disease state. And what we show is that we recover relative prevalence estimates, which are sort of higher among unmarried patients and Medicaid recipients. So Medicaid is sort of a specific type of health insurance in the United States, which is available to lower income populations. And we sort of show that those populations have higher relative prevalence estimates, and this is consistent with past work. The initial sample where we examine this is a bit weird, so we actually get 2 other samples and show consistent results there as well. To demonstrate the applicability beyond medicine, we also look at the relative prevalence of hate speech on an online forum, depending on sort of what subgroup of people it mentions. So we sort of look at what's the probability that a comment on an online forum is sort of a hateful comment if it like mentions a woman as opposed to a man, as opposed to no gender group at all. As you might imagine, anytime you start sort of mentioning someone's identity, that's like a bad sign. And so we do indeed find sort of higher inferred relative prevalence if you mention identity, and furthermore, sort of among marginalized identities. So to summarize, we propose relative prevalence estimation as a task in PU learning, which you can do even if you can't get the absolute prevalence. We give 3 assumptions under which this can be done, and we sort of show that the method works reasonably well on several different data sets. Future work here, I think there are other settings where you can sort of apply this besides IPV. I think long COVID is an obvious example of something which is really underdiagnosed, and we'd like to know what groups it particularly affects, but I think there are other settings as well. I want to make sure I leave a bit of time for questions. So I'm going to move on to the final story, and this is one of algorithmic bias. This is like very preliminary work. Until recently, it didn't even have a title. It's joint with Ziad Obermeyer and Anna Zink, and it's about whether we should use race in clinical algorithms. So as many of you may know, this has been a very high profile debate in the medical community. When can we use race as a predictive feature in algorithms? It's appearing in medical journals like the New England Journal of Medicine or whatever, but actually more importantly, it has like immediate implications for patient care in the sense that like hospitals are changing how they do business. Like they're changing how they do these computations. US senators are asking for more information. So this is not like just something which is like getting cited, it's something that actually matters. To give an example of this, for example, EGFR is an important measure of kidney function, and it can be computed from creatinine, which is a clinical measurement that you can take. But you have to do some sort of mathematical transformation, and historically, that transformation has been race dependent. It's been different depending on whether the patient's race is Black. And sort of hospitals have started changing whether or not they use this race correction, whether or not they do a race-specific calculation of EGFR. And EGFR really matters because it affects, for example, whether the patient is diagnosed with kidney disease, whether they get a kidney transplant, a whole bunch of downstream implications. So this is an example of like a setting where this is actually being done. EGFR is maybe the most sort of widely known example, but this happens in a bunch of other cases as well. And this paper I've cited at bottom provides a sort of laundry list of cases where this has come up. And so, there are good reasons that the use of race in medicine is being heavily scrutinized. These reasons include some race corrections have been based on extremely dubious empirical data, right? It's like tiny samples from the 1950s on non-representative populations with non-publicly available data, like all the stuff that would raise normal statistical red flags. There's concerns about exacerbating health disparities, right? If you include some term in your risk prediction algorithm that says Black patients are at lower risk of disease, then maybe they don't get screens that they would otherwise get. And given sort of disparities in screening which already exist, you might worry about exacerbating health disparities. And then finally, there's a long bad history of racist beliefs about biological racial differences, right? Race is a social category. It doesn't map neatly onto like biological notions of ancestry, but in spite of this, there's a long history of, clinicians believing, for example, that Black Americans needed higher doses of X-rays in X-ray machines, which you can imagine why that would be bad. The racial biases in pain assessment and sort of false beliefs that Black patients have thicker skin and stuff like this, so it's just, there's a long bad history here. All this to say, it's good and very reasonable that the medical community is revisiting these race corrections. At the same time, the consequences of removing race from these calculations remain unclear. And, removing predictors in clinical algorithms that are already being widely used on real patients and have life or death consequences is something that you probably want to do pretty carefully. And here's a piece in the New England Journal saying exactly that. Please refrain from haphazardly removing race. We need to understand what the actual consequences of doing this are. And in particular, our argument is that removing race as a predictor can have unintended consequences in some cases, and even decrease equity in some cases. And we provide a case in which this occurs when racial bias can create differential measurement error. So this is the link back to sort of missing data, which I'll now elaborate. So how does racial bias create measurement error? Well, it makes it more likely that some race groups will have critical risk predictors mismeasured. There are many examples of this across medicine. We've discussed some in this talk already, right? Racial disparities in testing and in diagnosis. And we have a review paper enumerating many other examples as well. The specific risk predictor we focus on is family history. This is a critical risk predictor. If you go to the doctor for a mammogram, they're definitely going to ask you about your family history of breast cancer, or at least they'll do this in the United States. I assume they do this in England as well. So it's very, very important to predicting a patient's risk. But a lot of previous work has shown that family history is more likely to be mismeasured in some race groups. We know that clinicians are less likely to ask non-white patients if they have family history. We know that non-white patients have higher rates of not knowing their family history. So for multiple reasons, family history is more likely to be mismeasured in some race groups, and sort of absence of known family history in some race groups may be far from reassuring. The patient may have a family history, even if it does not appear in the medical record. So we examined this on what's called the Southern Community Cohort Study dataset. It's was widely used to study race, to study health disparities, and it's quite racially diverse. And in particular, we study how colorectal cancer risk varies by race and family history. To sort of examine, how the differential predictive value of family history across race groups. So we find that family history is highly predictive for white patients. So this sort of shows rates of colorectal cancer as a function of age, because age is a very strong predictor. And you can see that for white patients, there's this really big gap where patients with reported family history have a much higher rate of colorectal cancer, as you'd expect. In contrast, in Black patients, this predictive relationship essentially disappears, right? The odds ratio is not statistically significant. And for those of you complaining oh, you shouldn't look at the individual odds ratios, you should look at the interaction term. Yes, the interaction term is also statistically significant. So why is this happening? This is totally consistent with what you would expect if there is differential mismeasurement of family history across race groups. Specifically, what we're seeing here is called, regression dilution, regression attenuation. Basically, if you try to regress cancer risk on family history and cancer history is mismeasured, that's going to bias the coefficient towards zero, right? Well-known statistical phenomenon. And if you want to capture this differential predictive value, the standard way to do so is with an interaction term between family history and race, and this is indeed statistically significant. So this is sort of the standard statistical correction for differential mismeasurement. It also results in more equitable predictions. In particular, if you fit a risk predictor which uses race in this way, it actually increases the fraction of Black patients who are flagged as high risk, and it does not harm the performance of the predictor. If anything, predictor performance increases somewhat. So to summarize, scrutiny of the use of race in clinical algorithms is very much justified. But removing race can have unintended consequences, sometimes paradoxically decreasing equity in spite of the good intentions of the people who are doing this. And we give a case study of family history, which illustrates this. A related point, that others have found is like, even if you remove race, the algorithm may reconstruct it anyway through proxies, right? Many of you may have seen this paper sort of demonstrating basically that AI can reconstruct a patient's race from their medical images, even under substantial perturbations and corruptions to those images. So simply removing race is no guarantee the algorithm won't sort of reconstruct it anyway. All of this sort of implies that the solution to racial bias in clinical algorithms is unlikely to come merely from excluding race. We show that sometimes this actually decreases equity. Others have shown that algorithms can often reconstruct race anyway. Rather, we think it's important to think carefully about the goal of clinical algorithms, which here is to predict cancer risk, and about how different algorithmic design choices might be more or less equitable with respect to different race groups with respect to this goal. So to conclude, I've told you 3 stories today, all about missing data and its connections to health and equity. And I think I'll close there to leave some time for questions. Very, very happy to chat about any issues you want to discuss. Thank you.
Thank you so much, Emma. That was a really excellent and thought-provoking talk. I'm sure there are lots of questions from the audience. If you do have a question, either just raise your hand using the I think the reaction thing at the bottom of your Zoom screen, or if you'd rather, if you can't speak, then just type your question in the chat and I can read it out. I can kick things off with I was curious about the COVID testing example. Was this based on people who were self-testing, or you said there were like biases in those getting tested, or what was the kind of like?
Yeah, that's a great question. This is based, so this was analysis done early in the pandemic, and it's based on data from Indiana, of sort of the state, which was one of the few states at the time that had test results broken down by race. This data came from like August 2020. My guess is that it's sort of, those being done at sort of PCR clinics, probably not people doing like home rapid tests, because those wouldn't necessarily be reported to the government. I actually don't remember offhand. But I think an important point you're raising here is that under testing here might result both from the patient's decision to not get tested and from the clinician's decision not to test them. And I think that is an interesting thing, which is not true in the policing case, right? Where it's really sort of the product of the officer's decision.
Okay, thank you. I've got like a bunch more questions, but I would like to give other people the opportunity to ask. I'm going to pause for a second. My next question was around. I mean, you make the case that in certain clinical algorithms, it's excluding race is not the right thing to do. Well, in some sense, but is there like is there a framework by which we can go through each of the clinical algorithms that are out there and make some sort of evidence-based decision as to whether it's the right thing to do to exclude race?
Yeah, I think.
Do you need a different process for which is kind of like domain specific?
Yeah, I think that's a great question. I think one nice set of heuristics which has been proposed, which I broadly think are reasonable. They sort of provide 3 heuristics. Where do we go? I'm looking for the reference for you. Yeah, I think in the hidden in plain sight paper, they provide a couple of heuristics, which I think are useful to think about at the end of the paper, which I think is useful. So for example, think about the quality of evidence on which, the race correction is based. Think about whether you're increasing or decreasing health disparities. But I think there are specific questions beyond that, and it's something I'd like to continue to think about, like how do you generalize this particular case study? Like, what does it really mean to think carefully about the goal of clinical algorithms? I think you're probably not going to be able to get to a setting where you're like, here is an exact algorithm for when you should or should not include race as a predictor. But I certainly think like correcting for differential mismeasurement is quite a compelling setting where you might wish to use it.
Yeah, I never thought about this issue of differential mismeasurement with respect to race. It's yeah, quite a kind of surprising. It's not surprising, but it's quite like yeah, impressive how it really does bring down the effect to zero.
It's quite dramatic.
Yeah,
It's quite dramatic in this data set. I agree.
May has a comment in the chat, says, thanks Emma for the great talk. Just a comment, seems like we have some way to go to change the discourse in official stats, health systems, etc. about simply excluding protected characteristics to avoid discrimination. These are great studies to use. Someone's just pointed out that I've got my microphone tilted up, and so maybe I was a bit quiet.
Is that the entirety of the comment?
Yeah, that was the comment.
Yeah, I mean, I will say I do agree with that. I think one way people think about it is sort of there are features which are like tainted, and like you don't, like there are features which are sort of biased in their measurement, and certainly, race is like there are features which are sort of, I don't know, they make people feel uncomfortable to use, and so their solution is kind of like, fairness through blindness. We're just going to throw away all these features that might be suspect. And I think that's you'll see that in the law, you'll see that in medicine. And like from a statistical standpoint, I think that is often not, from a statistician standpoint, that's often not quite the right thing to do. And so I think it's, people's intuitions here, I think don't necessarily serve us well. Yeah, I think it's I suppose something which is like important to avoid, right, is that just because you include race in your clinical algorithm doesn't mean that it's a biological like causative factor, right, in whatever disease or outcome that you're studying. And right. I think the measurement error one is like a really good example of that, where it's it's a problem with the data rather than anything which is kind of biological in nature. Right. No, I mean, there it's like race as a social construct is having real consequences for measurement. It's nothing about race. Yeah, exactly. Great. I think we're just about out of time. So I think we'll wrap up there. Thank you so much for an excellent talk. I can see people doing applause emojis. You did very well dealing with the feline fisticuffs in the middle of that talk. All right. No, thank you so much for the invitation. Cheers, and thank you everyone for attending. Our next webinar will be, I think, on the 15th of December, but look out in the newsletter, the December newsletter, for an announcement of that. Thank you again, Emma, and take care, everyone. Bye-bye.